Imagine hitting a strict performance plateau in your zero-shot forecasting pipelines. If you're developing models right now, you know the immediate reflex across the industry is to just, well, throw another billion parameters at the problem.
Right. It's just scale it up.
Exactly. You expand the context window, you burn way more compute, and you basically try to brute force your way across the lost landscape. But, what if that entire approach, that fundamental assumption that scale is all you need, is just completely flawed when it comes to time series data?
Yeah, and that is really the core premise we're analyzing today.
Hmm.
I mean, if you're working in the machine learning space, you've undoubtedly tracked the trajectory of TSFMs or time series foundation models.
Oh, absolutely.
Over the last year, we've seen architectures like Xi and times FM treating time series tasks virtually identically to large language modeling. They've just scaled their architectures up to like 1.5 billion parameters, specifically to drive down zero-shot forecasting error.
And our mission in this deep dive is to unpack a technical paper that, frankly, completely subverts that scaling hypothesis. So the paper is titled Reverso, Efficient Time Series Foundation Models for Zero-Shot Forecasting. It's authored by researchers from MIT, AI2, and Q Research.
It's a fascinating piece of work.
It really is. We are going to deconstruct how this architecture, using models ranging from just 200,000 to 2.6 million parameters, manages to match or even outperform those billion parameter giants.
Yeah, beating models that are orders of magnitude larger.
Right. So we'll explore the exact network design, the pre-training data strategies, and, the inference techniques that actually make this subquadratic efficiency possible.
So to really understand what Reverso is doing differently, we first have to sort of isolate the mathematical bottleneck that's inherent in existing state-of-the-art TSFMs.
Okay, let's get into it.
Because the vast majority of those massive models rely on standard decoder-only transformers. And when you're dealing with time series forecasting, capturing multi-scale seasonality inherently requires you to process a very long sequence.
Right, you need that historical context.
Exactly. But the structural issue there is that the self-attention mechanism operates with a quadratic computational complexity relative to the sequence length.
The classic big O of L squared bottleneck.
Yes, exactly. And that mathematically restricts the practical length of the sequence you can utilize during both pre-training and autoregressive inference. Before you just completely exhaust your GPU memory.
I want to pause on that, actually, that direct translation of LLM scaling laws to time series, because this seems to be where the core friction lies, right? Like, natural language possesses incredibly dense semantic information. Every single token carries specific isolated meaning. But time series data, conversely, is fundamentally continuous. It lacks that dense, discrete semantic structure.
Yeah, it's a completely different modality.
Right. So given that stark difference, why did the field assume in the first place that scaling multi-head attention up to billions of parameters was the optimal path for forecasting?
Well, honestly, it largely stems from just the sheer empirical success of transformers in other domains. Researchers naturally adapted the architectural primitive that was, winning everywhere else.
Makes sense. The path of least resistance.
Exactly. But the authors of Reverso argue that large-scale transformers are mathematically excessive for time series. Their core thesis is that you can achieve state-of-the-art recall and reasoning by highly optimizing a small-scale Model 1 that interleaves modern linear RNNs with long convolutions.
And by structuring the network that way, you bypass that quadratic computational bottleneck entirely, right?
Precisely. You bring the complexity down while fully preserving the predictive performance.
So let's actually dig into how they construct that subquadratic architecture, starting with how they handle the input sequence. Because the input handling here is uniquely minimalist.
It really is.
They take sequences of length 2048 and they enforce a strict normalization, right? Scaling the sequence purely between 0 and 1. They explicitly skip standard z-score normalization.
Yeah, which is unusual. Very. And then they linearly interpolate missing values and point-wise up-project the data to a higher dimension. But the architectural choice that really stood out to me is that they completely discard standard time or metadata embeddings.
Yeah.
They treat the input purely as an unembedded numeric sequence. Why strip out that contextual information?
So removing temporal metadata is actually a deliberate regularization strategy. By stripping away those external timestamps, the architecture is forced to learn intrinsic periodicities directly from the signal itself.
Oh, wow. So it can't cheat by just looking at the clock.
Exactly, yeah. It prevents the model from developing a reliance on specific, localized time markers. And that makes the representations far more robust and adaptable during zero-shot inference, like when you ask the model to forecast on an entirely unseen domain.
That makes total sense.
Right. So once that raw sequence enters the network, it hits the first half of the sequence mixing block, which is the gated long convolution layer. And instead of dense attention, they use depth-wise separable convolutions, right, where the kernel size is set equal to the entire sequence length, so k equals L.
Yep.
But intuitively, running a convolution with a kernel that massive across an entire sequence, that should incur a severe computational penalty. I mean, how are they achieving efficiency there?
Well, they avoid the penalty by executing the convolution in the frequency domain rather than the time domain.
Oh, of course.
Yeah, by utilizing the fast Fourier transform, or FFT, they transform what would normally be an immensely expensive sliding window operation into just a straightforward frequency domain multiplication.
Which brings the operational complexity down to log linear time.
Exactly, O of DL log L. However, a convolution alone, even a highly efficient one operating in the frequency domain, is still static.
Right.
It applies the exact same filter weights across the entire sequence.
Right. It can't dynamically adapt to new inputs.
Exactly, and that is where the alternating DeltaNet layers come in. DeltaNet is a linear RNN variant that introduces that dynamic, state-dependent processing that convolutions inherently lack.
So rather than reading through the raw algebra of the state transition formulas here, can you just explain functionally what that DeltaNet layer is doing to the hidden state?
Sure. Functionally, it utilizes a dynamic gating mechanism that basically serves as a linear alternative to standard attention. The mathematics dictate a specific forget gate.
Okay, like in an LSTM.
Similar concept, yeah. It determines exactly how much outdated historical information should be flushed from the constant size memory state.
Yeah.
And simultaneously, an input gate determines exactly how much of the new incoming data vector is integrated into that state.
Got it. So it maintains that constant size memory while dynamically updating based on whatever the current input is.
Precisely.
But time series forecasting often requires bidirectional context, though, right? I mean, you need to understand what comes before and after a specific data point. Standard RNNs are strictly causal. They only process forward.
Right.
So how does Reverso achieve that necessary bidirectional awareness without, breaking the causal autoregressive formulation you need for forecasting?
They resolve that through a technique they call state weaving. It's actually really clever. Instead of initializing each layer's hidden state from, like, a zero vector, they explicitly add the final time step of the previous layer to the current layer's first hidden state.
Oh, I see.
Yeah, so this operation weaves the global full sequence context gathered from the previous layer directly into the initialization of the next one.
So it essentially gives the network bidirectional awareness while strictly maintaining causality in the forward pass.
Exactly. It's a very elegant mathematical solution.
And following that sequence mixing block, they drop in a channel mixing module. This part is, well, it's relatively standard. It's a multi-layer perceptron with a dimension expansion factor of 4.
Standard stuff, yeah.
But I noticed they utilize standard ReLU activations here. Empirical ablation studies in the paper showed that this basic ReLU setup actually outperformed more complex gated linear unit alternatives, which I guess keeps the parameter count tightly optimized.
And that tight optimization sets up a really fascinating architectural pivot at the very end of the network. Because after systematically eliminating standard attention from all of those sequence mixing layers to, maintain log linear efficiency,
right,
the authors suddenly reintroduce a standard attention mechanism in the decoder head.
Okay, I have to admit, I genuinely don't understand this choice. I mean, if the explicit stated goal of the Reverso architecture is to eliminate the computational inefficiencies of multi-head attention, why introduce an attention-based decoder instead of just using a standard lightweight bilinear projection layer?
It seems weird.
It feels like a direct architectural contradiction.
It definitely appears contradictory until you analyze the ablation studies concerning long-range dependencies. Running standard attention across every single layer of a deep network incurs a massive compounding computational cost.
Obviously, yeah.
However, utilizing a single attention head strictly at the output decoder provides this critical boost to the model's ability to finalize global relationships. And it does that without ruining the overall efficiency budget.
Okay, so how does that single attention head actually operate on the transformed data?
So the final transformed hidden state, generated by the sequence mixing layers, is projected to generate decoder query vectors. And then these queries attend over keys and values derived from that exact same hidden state representation.
Interesting.
Yeah, it allows the model to predict an entire patch of data points, specifically 48 points simultaneously. So that single attention operation basically acts as a global routing mechanism to align all the local patch predictions before output.
Okay, that makes a lot more sense. And to train that setup, they use mean absolute error as the core loss function, and they incorporate NaN masking, which, handles variable length or corrupted sequences seamlessly.
Yeah, very necessary for real-world data.
Right. And there's also a notable divergence in how the different model sizes handle positional embeddings. I found this really interesting. The smaller 200K and 550K parameter models train perfectly without any positional embeddings at all.
Right, none whatsoever.
But the largest model, the 2.6 million parameter version, strictly requires explicit SYNCO's positional embeddings to converge optimally. What's going on there?
Well, that discrepancy indicates that the representational capacity of the 2.6 million parameter model is just large enough that it requires explicit temporal ordering signals to sort of stabilize that final attention head. Smaller models simply lack the excess capacity to require that explicit routing. They're regularized by their own parameter constraints. But, building a hyper-efficient, highly optimized architecture like this is a double-edged sword.
Because when you strip out heavy parameters, the model becomes incredibly prone to overfitting the training data, which forces us to look at how they engineered the pre-training phase to prevent that exact issue. Because they utilize the gift-evil dataset, which is massive. We're talking roughly 4.5 million individual time series comprising 230 billion data points.
It's a huge dataset.
But if you're working with gift-evil, there is a severe class imbalance problem. The dataset is heavily skewed towards specific domains, primarily building energy usage and weather data.
Right, there's just so much of that data available.
Exactly. So if you train naively on that distribution, your foundation model simply becomes like an overly optimized thermostat.
Yeah, it wouldn't generalize at all. So to counter that severe imbalance, the authors employ a strict stride recomputation strategy. They mathematically cap the maximum number of samples any single data set can contribute to 100,000 per epoch.
Okay, so a hard cap.
Right. And by dynamically adjusting the sampling stride based on the total temporal length of each specific data set, they enforce uniformly balanced exposure. So this mathematically guarantees that no single domain can dominate the underlying representations of those long convolutions.
They also rely heavily on sequential data augmentations to build robustness, right? The paper lists an extensive sequence of transformations, but two specific augmentations really stood out to me as critical for a real-world application.
Which ones?
First, sensor augmentation, where they apply clipping based on quantile thresholding. Basically, they're simulating sensor failure or ceiling effects, like when a physical sensor hits its maximum reading capacity and just flatlines.
Oh yeah, that happens constantly in the field.
Right. And second, vertical flips, which just act as strict sign inversion. But why are these specific augmentations so critical for the linear RNNs?
Well, time series data in real-world deployment is inherently messy and, non-stationary. Sensor augmentation forces the linear RNNs to maintain robust state representations, even when the incoming signal abruptly flatlines or loses variance.
So it teaches the model not to panic when the data gets weird.
Exactly. And vertical flips ensure the network learns relative relational dynamics, rather than simply memorizing absolute directional trends. But the paper definitively proves that even with these robust augmentations, real-world variance is basically insufficient for training these specific mathematical primitives.
Right, I saw that. They actually had to implement an entirely synthetic data generation pipeline using a framework called kernel-synth.
Yes, that was a huge part of the recipe.
They utilize Gaussian processes to generate purely synthetic time series. And this involves composite kernel banks, specifically combining radial basis function, Mathern, and rational quadratic kernels.
Very complex synthetic signals.
Right. They also inject synthetic spike processes and explicitly model trend, seasonality, and irregularity components to create perfectly structured noise.
And the ablation results underscore exactly how vital this synthetic data is. I mean, removing the synthetic data from the pre-training mixture degrades the model's mean absolute scaled error significantly. It drops from a highly competitive score of 0.738 all the way down to 0.786.
That is a massive drop in this context.
It really is.
Yeah.
Exposing the architecture to mathematically pure periodicities generated by those Gaussian processes is a strict requirement for the state representations within the long convolutions and DeltaNet layers to fully mature.
So pre-training establishes those robust base representations, but the true test of zero-shot forecasting happens dynamically at inference time. You need mathematical adaptation, especially when the target time series presents a seasonality that completely exceeds the model's fixed 2048-step context window.
That's always the tricky part with fixed windows.
Right. So Reverso introduces two specific inference time strategies to handle this limitation, starting with what they call flip equivariance.
Right. So with flip equivariance, the model processes the original context sequence and a vertically flipped or, sign inverted version of that context simultaneously. It runs a forward pass for both and then just averages the final outputs. And interestingly, the authors note an operational distinction here. Performing this averaging at every single step of the autoregressive rollout, what they call the flip every approach, actually yield marginally better zero-shot results than only averaging once at the very end of the prediction horizon.
Interesting, but I think the more structurally significant inference strategy is their FFT-based downsampling algorithm. Let's break down how this works conceptually, without getting totally lost in the raw equations.
Sounds good.
Because if an input sequence has a fundamental periodicity longer than the fixed context window, the model mathematically just cannot observe a full cycle. So to resolve this, the algorithm computes the amplitude spectrum of the input using an FFT to identify the dominant frequency peaks.
It's a brilliant mathematical bypass, honestly. But the model doesn't just trigger it blindly. There are 3 strict statistical criteria that must be satisfied before the algorithm will initiate downsampling.
What are those conditions?
First, the primary frequency peak must be significantly larger than the secondary peak. So P1 has to be greater than or equal to 2 times P2. Second, that primary peak must explicitly exceed the DC component, the zero frequency baseline.
Okay, so that ensures the seasonality is mathematically stronger than just the overall flat trend of the data.
Exactly.
Yeah.
And third, the peak must be statistically significant relative to the mean amplitude and standard deviation across the entire spectrum. Specifically, P1 must be greater than or equal to the mean amplitude plus 4 standard deviations.
Wow, okay. So if those criteria are met, the algorithm is essentially confirming there is a dominant clean signal existing outside the current context window.
Yep.
And it then downsamples the input data so that at least 8 full periods fit neatly into the context window.
Yeah.
The model generates its forecast in this compressed temporal space, and the output is mathematically interpolated back to the original high-resolution sampling rate.
Which fundamentally allows a small context model to reason over incredibly long time horizons. It's incredibly efficient.
It really is. So having established this hybrid architecture, the pre-training balancing, and these inference time optimizations, we have to evaluate how these theoretical design choices actually manifest empirically.
Right. Let's look at the numbers.
The authors tested 3 model variants. The Reverso Nano at 200,000 parameters, the Reverso Small at 550,000 parameters, and the standard Reverso at 2.6 million parameters. And keep in mind, we are comparing these against foundation models holding hundreds of millions or even billions of parameters.
And the zero-shot performance on the comprehensive gift-evil benchmark, it completely validates the entire architectural premise. The 2.6 million parameter Reverso model achieves a geometric mean MSE of 0.711.
That's incredible.
Right. This directly outperforms comparably sized linear models and state space models.
Yeah.
But the truly disruptive data point is the Reverso small model.
Yes, I was blown away by this. At merely 550,000 parameters, it scores an MASE of 0.726. To put that in perspective for you, this 500,000 parameter model is comfortably defeating heavily scaled TSFMs that are 10 to 20 times its size.
Precisely. And the success holds specifically in long horizon forecasting too. When tested on the LTSF benchmark, which covers the standard ETT, electricity, and weather data sets, the Reverso models consistently demonstrate superior mean absolute error.
Yeah, they generate tighter, more accurate long-range forecasts than models with massive parameter advantages. Like it specifically outperforms the 200 million parameter times FFM and the 1.5 billion parameter Shimax model.
This completely redefines the efficiency performance Pareto frontier in this space.
Yeah.
It proves definitively that for the time series modality, precise structural optimization and sequence mixing efficiency yields substantially higher returns than raw unoptimized parameter scaling.
Absolutely.
We are seeing a structural refinement in time series similar to how, Roberta systematically refined the baseline set by BERT in natural language processing.
Right. So to summarize the core findings for you, By systematically replacing the quadratic computational bottleneck of self-attention with the highly efficient complexity of long convolutions and DeltaNet linear RNNs, and of course supporting that structure with mathematically robust augmentations and FFT downsampling, a 2.6 million parameter model can effectively rival and beat 1.5 billion parameter baselines.
It's a profound demonstration of architectural efficiency over brute force scaling.
It really is. Which leaves us with a final theoretical question to explore. We've seen that combining these subquadratic sequence mixing primitives allows a sub-3 million parameter model to completely dominate in univariate forecasting.
Right, univariate.
Exactly. So what are the theoretical limitations and computational requirements of this hybrid mathematical approach when it's expanded to high-dimensional cross-channel multivariate time series? That is a domain where the dense cross-variable routing of full attention mechanisms currently dominates. If scale isn't all you need, we must precisely define where mathematical elegance hits its absolute limit.